property of del. Okay, let's say we are given the vector. Okay, the vector vector function. Okay, f and g. This one should be bold because the vector, right? Okay, so the capital F and capital G, they are vector function. Small f and y are scalar functions. Then we have the phi and the psi, where phi and the psi are constant, okay, which is scalar. So because of they are scalar form, so you can just, this one is a gradient. So whether you just compute the summation or the subtraction of the psi and the phi, and after that you evaluate the gradient, and the answer will be similar if you separate them. So the gradient of phi plus minus the gradient of psi. And for this one, psi and the phi and the psi, they are scalar. So and they are multiply each other, and the gradient here is vector operator. So how can you okay, so the left side means that you just multiply them first, and after that find the gradient, or you can do the separate one, which is using this particular formula. So this one is actually looks like just like, okay, I just say just like product rule. Okay, phi grade phi grade psi plus psi grade phi, and this one division, so it looks like the quotient rule. Okay, and then if you have the dot product, so you have f plus g, they are vector, so whether subtraction or summation, and then after that you obtain the divergence, or you can do the separate because they are plus minus, so you can find the divergence of f plus minus the divergence of g. Okay, and similarly for cross product we can also do the same, whether you just total them up first, or just subtract between f and g, and you get a new vector, and you compute for the curl of this new vector. Or you can use this formula where you find the curl separately. So find the curl of the f and plus minus the curl of the g. Okay, and this one, as I mentioned earlier, this is a special property where we give you a Laplacian operator. So you have phi xx, phi plus phi yy plus phi zz. So this is another also from my last video, which is from the previous slide. So these three properties has been shown before. Okay. So in this video, I want to share with you another example. Okay, here I give you another example where I'm taking this from a book. Okay, so you are given two vector field, and also you have a scalar field. Okay, so look at the question 1. Normally we have the cross product where the gradient is in front, right? But now you have the gradient over here. So now how can we do? Is it possible? Yes, possible, because gradient here is a vector operator. So when you have a vector and a vector, so if we have cross, meaning that it is valid. Okay, mathematically correct. So now how can we evaluate this where the gradient is after the vector f? Because if curl, it should be the gradient first cross the f, but now f cross the gradient. So this is not curl. Okay, so now okay, just to answer the first one. So in this case, you have f cross gradient. So what you have to do is just plug in I, J, K, I. Okay, so f is 2yz minus x square y and x square 2yz. Okay, and then the gradient is del x, del y, del z, del x. So now we want to get the x component. So we have minus x squared y and del z is at the back. Okay, so you cannot put in front here because here this is very sensitive on the of the location. So if you have the gradient first, then you have to put the del z in front here, but this one you have to follow the sequence. Okay, because we know that the gradient here is not just like a normal expression. This is an operator, so if it is at the back, then you have to make it at the back. Okay, so then minus xz square del y. Okay, so that is for x component. So now you go to the J. So you have xz square del x minus 2yz del z. And then for z, so 2yz del y plus x squared y del x. Okay, and then you have to multiply. You have a vector here, right? And you got a new vector, then you have to multiply with the scalar function. So when you have phi, okay, meaning that your vector del y minus x squared del del y x squared del x minus 2yz del z 2yz del y plus x squared y del x, then multiplied by the scalar function where it is 2x squared y z cube. Okay, so then we'll give you, okay, for the x component, minus x squared y, so del z of, just like you multiply this one multiplied by this, so this partial derivatives is for the phi. So 2x squared y z cube minus x squared del y of 2x squared y z cube. So that is only for x component. And then we go to the y component. So for y component, we have xz squared del x of phi minus 2yz del z of 2x squared yz cube. Then the z component, 2yz, 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 del y of 2x square yz cube minus x square y del x of 2x square yz cube. Okay, so then this one you have to differentiate with respect to z. So this will give you 3266 x squared y z square minus z square, and then differentiate this with respect to y, so you have 2x square z cube. Okay, now look at the second one here. We have x z square 4x y z cube minus 2y z 6 x squared y z square. Okay, and the third one, 2yz 2x square z cube minus x squared y 4x y z cube. So it looks like we need to simplify the form. Okay, so I found a mistake here. So this one's supposed to be positive because negative, and the answer becomes positive. And then when you simplify, and this is your result. So meaning that here I want to show, even though the gradient is at the back, because normally we have the curl. When we have the curl, so we have the gradient cross, right? Gradient cross F. Okay, but now you have the other way around, so still possible, but you have to bear in mind that this one is operator. So when you sort this, you have to make sure that okay, especially for, let's say, okay, I repeat, for the component I, so negative x squared multiplied by del z minus x z squared first multiplied by del y. You have to follow the sequence. Okay, that is because of we have vector here, so they are very sensitive with the location. Okay, so that is the thing that I want to highlight.